Okay, in this very brief lecture, we want to write down some more very important properties of a determinant. So in the last lecture, we saw how row operations will affect the determinant. These aren't really row operations, they're just some properties mainly about the product that you should memorize. In particular, item number one, if you've got two square matrices, then the determinant of the product is equal to the product of the determinants. So in other words, I'll say sometimes that determinants go through products, right? So the determinant of AB is the same thing as the determinant of A times the determinant of B. So the determinant symbol went distributed among these two matrices. And then what follows from item one is that if A is invertible, then the determinant of A inverse is 1 over the determinant of A. And the reason for this really is simple, right? If A is invertible, then you know that A times A inverse is equal to the identity matrix. And then you take the determinant of both sides. So when you take the determinant of this side, you get the determinant of A times the determinant of A inverse is equal to the determinant of the identity matrix. But the identity matrix is a diagonal matrix, so it's definitely upper triangular or lower triangular, and the elements along the main diagonal, those are all 1. So when you take the determinant of the identity matrix, you just get a 1. And so now if you want to solve for the determinant of A inverse, you just divide both sides by the determinant of A. So that's how we got this, right? So this formula really follows immediately from this formula. And then the last thing is the determinant of a transpose is equal to the determinant of the original thing. So the determinant of A transpose is equal to the determinant of A. So definitely want to memorize these three properties. And please avoid this following pitfall here. The determinant of a sum is not equal to the sum of the determinants. So determinants do not go through sums the way they go through products. Here is more on the fundamental theorem of linear algebra. So remember, we had this theorem that said all of these statements are all true or they are all false, except for statement number 6 here. So we've already seen that the first 5 statements are all true or all false. So now we can add a 6th thing to the list. And the reason we can add the 6th thing to the list is because of this theorem. A matrix A is invertible, right, has an inverse if and only if the determinant is not equal to 0. So this is the quick way, if you can compute the determinant quickly, to see if a matrix is invertible or not. And if it is invertible, then that means AX equals B has a unique solution for every B. It also, this statement is true. If A is invertible, this statement is true, then this statement is also true. This statement, AX equals 0, so the homogeneous system, has a unique solution. This must also be true if A is invertible. Conversely, if this is true, then we know A is invertible, right? This is if and only if. All true or all false. The fourth thing, A is invertible, is the same thing as saying that the reduced row echelon form of A is equal to the identity matrix. So if A is invertible, then that means you can carry out row operations and row reduce that thing until you get the identity matrix. If A is not invertible, then the reduced row echelon form of A is not the identity. In other words, what has to happen is you will have to get a row of all zeros. So that's really why this thing is true. And then if A is invertible, that's the same thing as saying that A can be written as a product of elementary matrices, right? If it's not invertible, then A cannot be written as a product of elementary matrices. And then finally, this theorem, A is invertible if and only if the determinant of A is not 0. In other words, if A is invertible, then the determinant is not equal to 0. If A is not invertible, that means the determinant is equal to 0. So definitely want to memorize that. And again, what is the reason for this thing? It's really because these two things say the same thing. If A is invertible, then that means A times A inverse is equal to the identity. And so we know that the determinant then cannot be equal to 0 because the determinant of A inverse is 1 over the determinant of A. It can't be 0. And then conversely, if you cannot put A in the reduced, when you take the reduced row echelon form of A and you don't get the identity, that means you do have a row of zeros. And what does that mean? That means the determinant must equal to 0. So if you cannot row reduce A to the identity, that means you will have a row of zeros, and that means the determinant will be equal to 0. So that's why all of these things are all true, in particular this one. But all 6 of these things are either all true or all false. Again, you need to memorize this theorem. It's called the fundamental theorem of linear algebra. So that means it's really important.